Okay, thank you very much. So I'm just going to talk about the process and the design and the element of collaborative working and data sharing involved in this project in the Bloomberg ramp. And I'm very glad to be here, but also the Bloomberg have allowed me to talk about this because this has been a kind of very confidential project that's still probably about 2 months away from kind of being finished. But it's basically, this is a picture of where it is. So it's St Paul's Cathedral in the front and the City of London, and it's literally right bang in the City of London, a stone's throw from the Bank of England and Bank Station, and it nestles into the medieval city, the city plan, and it's really a kind of it's been a kind of lavish focus on the quality of materials and design and detailing throughout the building. And it's really prompted by Michael Bloomberg's desire to create a building in which people are proud to work in and which inspires a culture of collaboration. Now the ramp sits, there's two buildings, a north and a south, and the ramp sits right in the heart of the north building. And this gives you, a sense of what it is. It's unique in the sense that on each flight it goes off in a different direction. So it's only by going up 3 flights that it actually returns to the same plan curve. And what you notice as well is that every landing, it's one continuous curvature going all the way up from level 2 right up to level 8. And as well as having a function of enabling people to move up and down the building in space, it also is an opportunity for, in terms of the passive ventilation strategy. The air coming in goes up through the ramp, through the atrium, out of the skylight above. And you can see here the relationship between the ramp and the atrium, and it really, the atriums kind of hug the ramp, but then open out, so that in terms of the total floor plan of the ramp, the atriums are much smaller per floor, but they rotate 120 degrees each flight as they go up. And then you get to this space which Bloomberg calls the pantry, which is a double height space. And the ramp literally flies out, and a bridge comes across to meet it where the landing is. And you see all of these, the kind of the ongoing process in design of the kind of visualizations and the dialogue with the client to really communicate what is actually quite a hard, a difficult three-dimensional form to get your head around. This is an animation that I created from the parametric model, and it really shows the versatility of the parametric model, where every frame of this animation is actually a fully detailed 3D surface model of all the cladding of the geometry. And this is actually where I started on the project. So this is 2012, and it's something that really bugged me. So I was looking at this and thinking, this isn't right. I don't know what you think about this curvature, but it bugged me. And just to explain, what it is, this is 3 ellipses that are tangent together. And what bugged me is that if you draw the central axis of these ellipses, that the point of where the tightest curvature, you see, you add the second one and the third one, and then you take away the rest. You see that on each leaf, as it were, of the ramp, you've got these 2 points of where the curvature is tightest. And actually, I wanted to define something that was one continuous curve, where as you're walking around, it gets tighter, 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 and then opens out again. You don't get these kind of 2 inflection points. So I managed to move from this, which is also the kind of the geometry of the skylight above, to this, and this made me kind of a sense of sigh of relief that I kind of got something that I was happy with. Now, actually, this journey was a kind of journey through mathematics, and this is the equation of a hypertrochoid, which is what the ramp is, and also the hypertrochoid defines the skylight above. Now, the mathematical equation might not be familiar with you, but those who grew up in the 60s or 70s probably familiar with the spirograph, and it's really just a process of rolling one circle around another, and you switch disks, and then you can draw the skylight. And I think this equation, this animation, again, it's just a way of explaining that it's starting off with just rolling a circle along a straight line. So this is a trochoid that it's drawing, and each time the arm of the circle is getting longer and longer until the point where you start bending that line into an arc and gradually curving it around until we finally get to the form, which is the kind of setting out geometry of the ramp. But then going beyond that, actually, the relationship between the skylight and the ramp, which are both formed from this same approach to curvature. So that's the skylight and the atrium around the top, around the outside, and then the ramp that draws itself up the center. So that's level 2 right up to level 8, and it's again all those frames are coming straight from the parametric model. So that's where this is where I started. So this is 2012, and actually, you know, what I'd learned from previous projects is it's the collaborative relationships, and it's that kind of workflow and building between disciplines that's key. And so when I started out, Foster's didn't have a parametric model of this, so I rang up AKT, who are the structural engineers, and said, have you got a parametric model? And they said, yes. So I said, can you send it to me? So this is what I got. And actually, there was this fantastic collaborative relationship where we went from this, which was still kind of defining these 3 ellipses, and 10 days later it was kind of this, and gradually I'm trying to kind of build in a kind of a set of logics, and actually this is the big shift, because from here you can see all the clutter somewhere up. Does this work? No, somewhere. Oh, there we go. All this, which was defining the arc, actually got pulled into to this setting out. And what this is basically all the variables on the left, all the parameters, and this top bit was defining the cladding. So this was the part that was owned by me, and the bottom bit was defining the steel structure, which was domain of AKT. And what you can see here is actually that the logos of AKT and Foster's actually appeared in the script or in the definition. But it's, you know, this process of collaborating, you see this email from 2012, and it's almost exactly 5 years ago. And you know, it's a process of, we tried to open your definition, but we're getting the following errors, which next day was, we tried, a different version, and we still get an error. But, it's that process of collaborating is about kind of defining naming conventions. It's agreeing parameters. They were using VB within scripting within Grasshopper, so I adopted VB so we could have a common language. And it's really this kind of this element of trust. It's kind of this level of skill and dialogue, as well as this kind of rigor of approach. So going through there, go right to the middle, and you see the hypercrocoid, which everything is coming out of. And actually, that change in the geometry was facilitated, and by this kind of magical moment in Grasshopper where you take something out of one thing and plug it back into another. But because their structural model was actually built in the same definition, that I could actually change the geometry, and all their model would update instantly. So what happened was, rather than spending 3 weeks then having coordination meetings of kind of updating their model, their model was already built into the analysis model. So that's their analysis, and so instead of wasting that time on coordination, they were able to really invest it in doing a kind of an exploration in dynamic response factors. So they tested all 96 steps, and for as they're excited, and really read the results over the full height of the ramp, and created a matrix of data that could be processed and analyzed, and interrogated the results, and actually got some surprising peak response levels in unexpected places. But it was this, that that level of collaboration where you've got a coordinated model between the two disciplines. So this is the structural model, and what's extraordinary is that the piles, I think, are some of the deepest ever in through the London clay. But you see the ramp structure going up in the heart of the building. Now, while this was going on, the 3D one-to-one prototypes being made to test the fabricator's capability. These guys in Germany didn't manage to pull it off. So the panels were then commissioned from a company in Japan. And then while that was going on, then they were already going ahead fabricating the steel. So this is in Littlehampton Welding in the south of England, and you can see literally the scale of this thing. It's vast, and every time we saw the mock-up, we saw this. It really, you design something, but you're completely taken back by the scale of the thing. And you can see it's also this isn't digitally manufactured in a fab lab. This is kind of men with steel and angle grinders and everything. So this is 2014, yes. So you can see that's where the ramp's going, right in the middle, and it comes onto site, and you can see St Paul's Cathedral just overlooking the building site, and here it's because it's bounded by the City of London. There's nowhere to store this, so the ramp structure was stored in situ, and gradually kind of it went up floor by floor. And you can see Norman came along to keep an eye on the proceedings. And here you see that 120 degree twist as it goes up. So literally, as the building was built, the ramp came along and was propped up on these goalposts, as you see. And then once the floors had been finished and the concrete poured and the rest of the building settled, then it was actually kind of bolted into the superstructure. So that's where it starts in level 2, going up to this double height space and up into the skylight above. So in terms of sharing data and logics with the structural engineers, AKT, we actually shared that parametric definition. Now, in terms of sharing data with the contractors, we use this approach, which is the kind of Lego instructions. So what we did is we encapsulated all the geometry, and because it's kind of defined by a series of mathematical equations, we could do that. And so this is the list of all the parameters for the whole ramp. You have a kind of, and then we had literally, I think there were 93 steps that we could go through with a series of kind of checking points. And the other thing, I've talked about the plan curve, but here, this is the curve in profile. And again, I turned to mathematical equations, but actually didn't just rely on this kind of mass per se, but actually this we put it into the VR because we wanted something that wasn't mathematically optimized, but actually that worked optically. So what we were trying to do, you can see here, you've got the landing. In this case, the curve of the handrail actually just travels right through where the landing is. So in order to reduce the height at the top, we actually subtly curved in a sort of S shape the geometry of the stair. But actually we didn't want anyone to see that. So what we've done is we're kind of playing off the curvature in plan with this kind of slight S-curve in profile. And it's really looking at 3 different options in VR and seeing where can we have the maximum S-curve that you actually can't see at all. So again, you can see this is the unrolled cladding. So that was the relationship with the cladding contractors, and we go through this, which is in the geometry method statement, to this, which came back and then got fleshed out to a kind of fully solid model with the bolts and everything, and we came within, I think it was 0.04 of a mil. No, yes, 0.04 of a mil of difference between their model and mine. And then these are the kind of complementary sort of architect's drawings that turned into these kind of fully fleshed out kind of bolts and everything drawings from the contractor. Now, the next step was kind of illustrated by this, which is, this is not a photo, and what's amazing about this is it's in a way the only chance you get to see the ramp in its entirety, because this is there were actually 2 point cloud scans done of the ramp, because with a shape this complex, it's how do you know whether it's in the right place or not? And so it was scanned. You can see here some of the goalposts that were used to support it. So this was the scan before it was welded into place, and here you see it again. And then this is the scan after it had been welded into place. And these were guys who were used to scanning nuclear submarines or kind of small machine parts. And taking on this kind of vast job where I think we had a billion points in this point cloud, which was then kind of decimated or reduced down to 24 million, which they gave to me. So this was the analysis I did, and really trying to determine where the data was in relation to the design geometry. So what I did is this was in 3D, and then I effectively unrolled this point cloud so you could kind of see in 2 dimensions, and colored it according to the blue is where it was kind of in the zone of where the brackets were. The red was if it was in the zone of where the honeycomb, and then the yellow actually would have been protruding through the bronze. So it gave us an indication of kind of where the issues were and what we had to do. Now, so while this was going on, the first shipment of panels came back from Japan. So this is Tilbury Docks in the Thames, and so we were inspecting the quality of these. And they're really exceptional in the finish. So it meant we had a dilemma, because the steel was slightly out of tolerance, so that we're talking about kind of 24 mil at a maximum. But it meant that the cladding panels couldn't fit on in this kind of pure theoretical design geometry position. So the next exercise was kind of how can we use that scan data to position, to reset out those panels so that they fit precisely over the steel. And this was this exercise, and because there's 10 mil gaps between each panel, we could shift these blocks of panels subtly so that you might go down to 9 one side or up to 11. And so we went through a series of iterations of just jiggling a little bit these panels in order to fit over the structure. So using some very sophisticated kind of measuring techniques. So you have here a laser tracker that was used to direct a handheld target to get the position of the top brackets within, sub-millimeter precision. And here you have, this is the solid model from the contractor versus, the key protruding parts of the of these bolts from the steel structure that were used as a kind of clash detection in order to get the position as tight as it could to the design geometry. So there you see these brackets that then the cladding panels are literally kind of hung on. And as soon as there's a panel coming out ready to go on the brackets, and as soon as these things were hung, they were covered by this. It looked like a kind of snow sculpture or something. These things had come all the way from Japan, and they were so expensive that they were afraid that anyone would kind of dent and scratch them. So we had moments where we came for a snagging inspection, and then the next time we came, they'd all be covered up. So we got these kind of glimpses of it, and actually, what's interesting is you're talking about data, and we had all these 3D models, these kind of instructions, and also these kind of there still were some architectural drawings, but the other key thing was the these specifications, and some of these numbers that were defined were actually the sort of the last line of defense for us to kind of snag and to measure and to actually push the installers to kind of to make some kind of final adjustments. So this is what's there probably a few months ago. So you're seeing the kind of the thing taking shape, and I'm just going to end in this video, which is this is available online from Bloomberg London's website, which just gives you a little glimpse into the building as it comes to completion. So that's the view of St Paul's that you can see from the building, and that's Michael Bloomberg walking down the ramp itself. And then the next shot of him, you'll see in a moment, him sitting in front proudly, sharing his philosophy. Thank you.
Thank you very much, Jonathan. I think this is a nice way how to, we've seen a lot of bits and pieces this afternoon, and we end with an architectural project, which was also not an easy task to get it into the data farming. But you've done it well also to connect indeed with data. There's lots of different items that we need to look at. There's the visualization, the analysis, which points do we analyze, and who's choosing, yes? Because you created tons and tons of data, but you also had this question of who's making the choices at some point in your project. So could you develop a little bit further, like at what point the engineers and yourself, like with the data, you have one common shared file, who's taking decisions, who's making it, getting forward?
Well, I mean, I guess, you know, you take you lead with decisions about different things. So, you know, in terms of the design, we were certainly, if not dictating, then really kind of steering that. But then, you know, it's a conversation. So, you know, some things are possible, some things are not. So there's some details which I haven't focused on where you're really wrestling with back and forth, and you know, these pinch points, because the ramp, it's about 30 meters between landing to landing, and there's one hangar midway, and that critical point was this. You know, it was even at the point of fabrication, they shaved bits off, and you know, it's this process of really trying to kind of extract the most out of it. So, you know, bringing the structural engineers back onto site to look at it, and then, you know, assess how much they shaved off. And you know, so it's this constant conversation of kind of trying to push and push and push to kind of maximize the, you know, all the opportunities from all sides.
Sure, but you're taking it in your hands, which is quite interesting in the fact that architects, there's tons and tons of data being produced every day, everywhere, right? And we've seen some examples this afternoon, what you can do with it, how to try to visualize it. And what you did or what you try to do is to take it into your hands, because all our data at the moment, they're somewhere stored in Google headquarters or something. And actually, you're trying to take a domain back at a certain point. It's not exactly on Google data, but if we're not watching out, probably IBM is going to design our future cities, of course.
Well, I mean, I think one of the other things is that all that point cloud data that you saw kind of beautifully visualized is actually, my first question was, can we trust it? And it's interesting because the cladding contractor did another survey with a separate company. And so the first question I asked when they got it back is, do the two match? And no one had thought to ask that question, but they looked and they didn't match. And so they went back and resurveyed and found that the three setting out points for you know, first of all, that the building is shifting, but the three setting out points had either moved or somehow the registration had gone wrong. So the analysis that I did actually had to be retranslated, because, you know, so I think it's really important that whenever there is data, even if you know, it had an integrity between itself, but actually it was slightly off in terms of its alignment. So I think it's the key thing is to always question the data and ask questions of, you know, it's.
Great presentation. I had a kind of a follow-on question. I think your presentation reminds me of the talk Chris Mackey gave this morning about tools versus toolkits. And it seems like the initial, maybe I'm wrong, but the initial ambition of the Grasshopper script was this kind of one tool that enables a collaboration between you and the engineer. And I wondered how that tool, the script, played out throughout the project, through the fabrication and engineering phase, because I kind of got the feeling that there was multiple tools ended up being used. You said you mentioned architectural drawings, fabrication drawings. So I'm wondering how many tools you used in the end to get it fabricated, and whether having a contractor that didn't work with the digital model was a hindrance. Was that? Would you prefer?
Well, the contractor did work in digital model. They built their digital model from the geometry method statement. So they basically built, in some ways the same parametric model, but something that they owned entirely, and that we'd kind of transferred, not just some dead geometry, but actually the logics of how it all fits together. So when there was discussion and some parameters were adjusted, that they could update in their model, so we by embedding the logics further downstream into the contractor, we could still in a way influence the geometry in the way we wanted, as it went. So actually that's probably enough to.
No. I think we would take the discussion maybe to another place, but I would like to finish this session, and also there's a way of handling all these data. We've come from sociological treating data and capturing censoring data, using it in projects, having people working together with it, collaborative working in this field of architecture. And somehow it is still my feeling, I'm a professor here working with students, that we are missing out on a big part of this data gathering, sharing, analyzing, abusing, basically, and we're not really discussing about it. In the whole field of architecture, no architect is going to start to talk to you about data, usually. And I think it's a possible danger. And that's what I would like to give you with as a thought to discuss about later this evening. We're going to have a couple of short conferences. Thank you, Jonathan.